All right, so let's start actually having a class. So kind of going through preparing for this class, I sort of thought, oh, it might be a kind of opportune time to just have a little mini discussion of de Rham cohomology. So some students have expressed a little discomfort with the concept, and it's an important thing to discuss. So let me give my really short discussion of it. So you start with a smooth manifold, and you look at the space of smooth K forms on that manifold for all K. And then you have this operation of exterior derivative, which sends a 0 form to a 1 form to a 2 form, etc., and has this very important property that when you do it twice, it becomes 0. So this is somehow dual to the operation of taking boundary of a submanifold. So one of the sort of explanations I had for how to intuitively think about pullbacks is a K form is something you can integrate over a K-dimensional submanifold and get a number. So sort of something about the space of K-dimensional submanifolds is dual to the space of forms. I mean, obviously take that with a bit of a grain of salt, but a lot of things about forms can be kind of explained in that language. So the fact that you can pull back forms corresponds to the fact that if you have a smooth map, you can take a K-dimensional submanifold and apply the map to it. And, okay, you might not get a submanifold, but there's some larger class of things that make sense to integrate forms over, which will be preserved by that. I think the easiest thing to say is smooth maps from K-dimensional submanifolds, from K-dimensional manifolds, submanifolds being a special case of those. All right, so if you're used to thinking about a complex where you have cycles, would be the term in algebraic topology, or submanifolds, and you take boundaries of those and then look at that chain complex, you get out a thing called homology. So when you do the dual thing with K forms, you get cohomology. Yes, Josh. You're muted. Did you intend to raise your hand?
Yeah, sorry. I was just asking about that if manifolds, submanifolds are dual to forms, I guess you'd like to view certain kinds of submanifolds as forming this kind of homology or something.
Yeah, exactly. So I'm being a little vague here because if you want to kind of get fancy about it, you shouldn't really think about submanifolds. You should think about chains and get into all of this homological stuff that I don't want to worry about. But that's kind of, if you know that story, you should think about the reason cohomology shows up here is that you can integrate forms over chains of the correct dimension or over submanifolds. This cycles, I think would be the right term there. All right, so by definition, I'm not going to write the sub-de Rham because I'm not going to talk about any other kind of cohomology in this class. Some people would write like a sub-dr here, or I think that Canis de Silva actually writes the word de Rham. Is you look at this complex, you look at the forms which are killed by taking this exterior derivative. So that's closed forms, and you mod out by the ones that are the image of taking exterior derivative. Those are the exact forms. The de Rham cohomology is the quotient of the closed forms by the exact forms. And again, this sort of isn't a main topic for this course, so I'm not going to get into why any of these are true, but feel free to ask in the notion, etc. So if you know any other way of constructing the cohomology of a manifold, like cellular or singular cohomology, this is the same. It's canonically isomorphic. And somehow the reason has to do with being able to integrate K forms over chains. one interesting consequence of that, which is not at all obvious from this definition, it's finite dimensional for a compact manifold, and for any reasonable manifold. One kind of useful way to think about these closed and exact properties is that being closed means that whenever you're integrated over the boundary of something, so you have a k-dimensional submanifold, or more generally a k-cycle with a boundary, you integrate over that boundary, and a closed form will give you 0, and you can prove that the converse is true. If your integral is 0 over all of those boundaries, then you are closed. And on the other hand, being exact, and in both cases I'm just using Stokes' theorem, being exact means that integrating over anything with trivial boundary gets you 0. So somehow the difference between closed and exact forms is exactly detecting whether there are cycles in your manifold which are closed, have no boundary themselves, but aren't a boundary, right? So the classic example is like R2, pull out the origin. Now the circle, the unit circle, isn't the boundary of anything because the disk isn't a submanifold of that. I should say boundary of something closed, right? If you try to apply Stokes, right, the circle, it is the boundary of kind of everything on the inside of the unit circle, but that's not compact. And so you can't apply Stokes' theorem there. The integral over the inside will be infinite. All right. Cool. Okay. So the other thing that's going to be kind of important for us, this maybe like seems like a slightly obscure point, but it's part of the reason that I'm going through this, is it's unchanged when I do a smooth deformation retract to a submanifold. So let me just remind you what a smooth deformation retract is. It's a map from the interval times my manifold M. So this is, I have an ambient manifold M, and I'm taking a submanifold N inside of it. And it's basically for every point in M, I specify a path that pulls it down to N. And if I was already on N, I have to just stay in place. So sort of the picture of this is, here I have N, and I can start anywhere, and I have a choice of path where I'm at my original point at time 0, and I go down to N at time 1. And I do this in a sort of continuous way for every point in the ambient space. So the way I can express that is, oh shoot, I had meant to, I kept trying to match Candace de Silva's notation and kept getting confused about what she was calling things, but I believe she calls this rho. So it's a map that goes from, sorry, M cross I to M. And I think of the I as being a time coordinate, and at time 0, it's the identity. And at time N, it's a retract onto M. It's a map to N that's the identity on the subspace itself. So at every point in N, I just stay in place. So if I start on N, I just stay in place. And if I'm anywhere else, I do a path that ends on N. And I have to be sort of smooth at every point. So I'm doing all of this in sort of a way, whereas if I move my initial point around, what this path is varies smoothly. All right. And this is going to be a useful thing for us. So let me just explain at least a little bit of why this doesn't change Durham cohomology. So by the proof of this, I mean invariance under retract. Invariance under deformation retract. So, well, what I can do is if I have a form on my ambient space, I can pull it back to N, and then I can pull it back by this map row of 1. So let me just remind you, I have I, the inclusion of this submanifold N, and then row 1 is a map from M to N, and these have the property that if I include first and then do this row of 1, that's the identity on N. So this is a kind of idempotence property, or you could think of it as a section condition, that this is a section of the map of, yeah, well, you could, but it would be a little weird. Anyways. Okay, so I compose these in the other order, and I pull back by them. So the claim I want to make is, sometimes I write these things out and then I'm like, oh no, I should have said that thing first. So these maps, these induce maps on forms. So I can pull back a K form on M to a K form on N. Rho I inverse goes the opposite direction. And I want to prove that these are inverse isomorphisms on homology. On cohomology, I should say. Theorem cohomology. Okay. And if I do this composition, that's definitely the identity because of what I have above. So I'm just using functoriality of pullback, that if I pull back by this kind of projection down to N, and then I've got something on all of M, and then I pull back to N, well, I get the original thing back because the map was the identity on it. What about when I do this in the opposite order? So I have to think about what composing these in the opposite order does. So I have to compare this guy with C. And of course, they're not going to be equal. When I pull back to N, I lose information, right? So C and C prime will go to the same place under doing I star first and then row 1 star, if they agree on N but are different somewhere else. So what I have to prove is, okay, yeah, those are different, but they give the same cohomology class. So I have to show that the difference is going to be exact if my original form was closed. And I do this using a homotopy operator. So I apologize for some people who've done algebraic topology, this is going to be like, oh, yawn, homotopy of a chain map. And for some people who haven't, it's going to be like, oh, what the hell are you doing? But I have this slightly strange operator, which is I have my deformation retract row, and here I have my VT, which, as it's always been, is the derivative of the flow. So VT composed with rho T is equal to ddt rho T. And I do this kind of integral. where I take my form, I contract it against the velocity vector as I'm traveling down towards n. I pull that back to my original starting place, and I integrate those. So maybe I'll actually go back to my picture. What I'm doing is I'm constructing a form here at m, which is gotten by, I go along this guy for some amount of time. I look at C here. I contract it against the velocity vector here. And then I pull that back to this original point. So this is going to give me a form 1 degree lower on my ambient manifold M. So let me come on, guys. Okay, I'm just getting, things are really laggy. All right. So what I'm getting here I'm kind of wrote in the underlying point to emphasize what's going on. I want to find the value of this form at m. So this is a k-1 form on m if C is a k form. And what I'm doing is I'm looking at the point rho t of m. I'm evaluating the form, the k form C there. I'm contracting against the velocity vector, and then I'm pulling back so I get a form at m instead. So each thing that shows up in this integral is a form sitting in k multilinear map from the k copies of the tangent space at m to the real numbers, and I'm integrating those in the usual way. So one thing I think it was clear a few people were mixed up about when I talked to them at office hours is about taking time derivatives and space derivatives. So right, when you're in a manifold, taking space derivatives is a really kind of fraught thing. You have this exterior derivative that's a weird coordinate independent thing. Otherwise, you have to say what direction you're doing things are. But when you have something that depends on time, like if it's an element of a vector space, for example, you can just take time derivative and get another element of that vector space. So here, and similarly, you can integrate. You can, if you have a time-dependent element of a vector space, you can integrate over time and get another element of that vector space by, Riemann sums, etc. All right. So here, that's exactly what I'm doing. Everything that shows up inside this integrand is an element of the vector space of k forms at the point m. I integrate from 0 to 1, and I get a k-1 form. It's k-1 because I contracted against the velocity vector. All right, this is a slightly strange formula, but it's a really useful one. So, I mean, I know this is a little like weird, as I say, for some people, it'll be like, oh, yawn, blah, 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 vector calculus. And for some people, this will seem really strange. But this is a really useful formula. Knowing that an operator like this exists is very useful, even if we don't really worry about what the exact formula is. So we get this cool theorem that the difference between Xi and this sort of weird pullback of pulling back to n and then pulling back by the retract, the difference between those can be written in terms of this operator Q. So either you do Q first, that lowers the degree, and then you do exterior derivative, that gets you back to being K form, or you take exterior derivative first, and then you do this operator Q. So in fancy homological language, we would say that the identity minus this pullback is null homotopic. Via Q. So Q is the homotopy. This is an algebraic notion of homotopy that sort of corresponds to what's happening if you have a homotopy in your underlying thing, right? So if you're kind of used to homotopy language, right, one way to say what's happening here is the identity map on M is homotopic to the map projecting from M down onto N. This deformation retract, that's a homotopy between those two maps. So if you're used to kind of abstract algebraic topology, I'm telling you the spaces M and N are homotopy equivalent. And this formula is kind of how that manifests on de Rham cohomology. And yeah, in the interest of time, I'm not going to get deep into this. We're already 25 minutes through class. But it's one of these things, it's such a beautiful idea, I don't want to completely skip it. It's enough to check that these two forms give you the same answer when you integrate over a K cycle, or you could say a K submanifold or K chain. And you apply Stokes' theorem to that submanifold times the identity. So I can pull back C by this flow rho, and I get a K form on M times an interval. And I look at Stokes' theorem applied to S times the interval. So on one hand, I can integrate the exterior derivative over the interior. And that gives me the term Q dc. On the other hand, I can apply Stokes' theorem and integrate over the boundary. And the boundary kind of comes in three pieces. There's the copy of S sitting over 1, there's the copy of S sitting over 0, and then there's the copy of the boundary of S sitting over the whole interval. And those pieces separately give me the terms C, this weird pullback, and then the other half of the homotopy minus D, Q, C. And there's a kind of picture illustrating this. The way kind of Q comes up is when you integrate over either the whole interior or the boundary times the identity, you can do a partial integration over the direction of that interval. And that's exactly what Q is. All right, cool. So yeah, that now tells us that rho 1 star and I star induce inverse isomorphisms. The most important example of this for us is going to be the most obvious one, which is if I have a K form on Rn whose derivative is 0, and just to simplify my life, I'm assuming K is bigger than 0. I have to worry about constant functions if K is 0. If it's exact, if it's closed, then it's exact. And I have an actual formula for the antiderivative. So somehow one of the reasons I thought it was worth going through this is it's not just that it's the exterior derivative of something. I have an explicit formula which depends on in a smooth way on C for the antiderivative. Yeah, Denny.
So normally we want to integrate the these guys over chains, right? But you're telling me that we can integrate over submanifolds instead. So are you telling me that the that we can represent something like homology classes can be represented by submanifolds? Wait, Ben, you're muted.
You're still muted.
I'm kind of deliberately avoiding questions like that. So I think it would be better to not say submanifolds, but maps of submanifolds, right? So it's very difficult to figure out when a homology class can be represented by an embedded submanifold. But I think maybe you can always represent it by an immersed one, right? That somehow like the hard part is avoiding self-intersections, and self-intersections wouldn't change anything about what I said here. So
Okay.
like, you can either just say chains and, because I understand what chains are, I know how to integrate K-forms over them, or like, so there are sort of various different ways. I was trying to not get bogged down in technicalities like that.
Okay, but it is true for immersed submanifolds. We can represent it.
I think that's right. Sounds right.
Okay.
Right, somehow like, yeah, I mean, I think any chain you can probably deform to be immersed.
Okay, I wasn't aware of this. Thank
you. Yeah, and I am deliberately saying that I'm not trying to get any of those details right, so don't quote me on them. Somehow the important thing is just like, that you should think of forms as dual to something like chains or submanifolds or cycles or whatever kind of technical thing you want to say, because you can integrate everything. That was kind of the only point I was making. All right, cool.
Can I ask why you've written an underline under the X of when you're defining row T in the blank array line?
Oh, yeah, where is that? Oh, I mean, I just want to emphasize that it's a vector.
Okay.
Yeah, it's probably unnecessary, but yeah, that's just what I write instead of writing the overline.
Okay, thanks.
All right. So that was kind of a little side discursus, but I thought it was worth covering. So let's get back to some symplectic stuff. So we talked last time about the fact that it's very hard to deform symplectic forms, right? If I have a compact a manifold and two isotopic symplectic forms, they're strongly isotopic and in particular symplectomorphic. We use this kind of Moser theorem where to construct the symplectomorphism between them, we kind of integrate it, right? When I was talking in office hours last night, this kind of came together for me, and I sort of didn't say this in class before, but what you're doing is you're trying to construct a symplectomorphism. You try to construct it as kind of an integral of a bunch of infinitesimal contributions, which in kind of our terms means you try to find the vector field, which is its derivative at any point, and then find the actual symplectomorphism by solving a differential equation. And the kind of cool thing is, out of how the symplectic form changes, you get the differential equation you need to solve by some relatively simple manipulations, which we'll talk about at least one more time. So you can try to implement this idea on a non-compact manifold, but you're going to end up in trouble because you end up with a vector field that might not actually integrate to a flow. So this is basically, you try to construct your symplectomorphism as some kind of integral, and your integral doesn't converge. It ends up being improper and everything goes wrong. But that doesn't mean that we should just kind of forget about the Moser trick. So one of the reasons that this Moser theorem is covered early in the book is there are actually sort of several interesting theorems you can prove with this Moser trick at the heart of them, but using slightly different technical setups. The one that I think is most important for us is what's called the Darbuth theorem. That if I have a symplectic manifold, then for every point, I can find a neighborhood around that point and coordinates on that neighborhood that make my symplectic form look like the obvious one on R2n, or if you prefer, on the cotangent bundle of R. So I'm always symplectomorphic locally around a point to the standard symplectic form on T star Rn, kind of the one describing the phase space of a single particle. So locally, all points in all symplectic manifolds look exactly the same. The only invariant is dimension. All right, and indeed more explicitly, I can say on this open subset, there are coordinates x1 up through xn, y1 up through yn, such that this point that I've started with goes to the origin, and the symplectic form is dxi wedge dyi, all summed up over all I. So this sort of tells us that symplectic manifolds have no interesting local invariance. It's kind of an interesting property. The only thing that's going on is that sort of distinguishes between them is global behavior. And again, this relies on the Moser trick, but you have to apply it in a slightly different way. So I fixed my point and I look at its tangent space. So that's a finite dimensional symplectic vector space. And so it has a standard basis, E1 up through En, F1 up through Fn, right? And so I'm starting with, well, the tangent space itself has a symplectic form, and because that's a linear one, I already know that it has to have this kind of standard form. I have this nice basis where I can write things out. Okay, so now I want to compare the manifold with the tangent space. The usual trick for doing this is you pick a metric on your manifold. You can always do this by usual partition of unity story. And so that induces an exponential map from the tangent space to the manifold. And for some small neighborhood of the origin, that exponential map is a diffeomorphism between that neighborhood of the origin and the neighborhood around P and N. So if I go far enough out, things are going to run into each other and I'm going to have problems. But for a small neighborhood around the origin, that map is an isomorphism. This is kind of a very, very common kind of argument that you can compare the manifold with the tangent space. So the basis we chose on the tangent space induces coordinates on the tangent space by the dual basis. And so it induces coordinates on this manifold via the exponential map. And I'm going to call these x1 up through xn, y1 up through yn. So these are not the coordinates I want from the Darbuth theorem, because things might start going wrong as soon as I go away from my point P. So I told you nothing about what this metric is. And depending on what metric I chose, I might get kind of very different looking exponential maps that might, squash things in one direction. And I made no effort to make this metric compatible with the symplectic form. So there's no reason that these would be the Darboux coordinates on the nodes. But on that neighborhood, I can use them to construct a symplectic form. So basically what I'm doing, I'm thinking of the tangent space as being symplectic in the obvious way. It has that symplectic form that looks kind of constant. And then I'm transporting that over to a neighborhood around my point via the exponential map. And that gives me another symplectic form, omega 1, on that neighborhood. I changed my mind about whether that should be omega 1 or omega prime, and I didn't fix it in my notes. Okay. So now that I have my neighborhood around my point, and I have two symplectic forms on it, I have my original symplectic form, which I'll call omega, or omega 0, and my new one, based on just the coordinates on the tangent space, that I'll call omega 1. And the question is, well, one of those has the form I want, the Darboux coordinates. Omega 1 does by definition. omega 0 is the one I started with. I wanted to show that that one had Darboux coordinates. Well, are they symplectomorphic? If they were symplectomorphic, then that would give me Darboux coordinates for my original guy. Well, the advantage of doing this, making my statement about one neighborhood of a point. So the thing I kind of give up when I stop being compact anymore is I'm not going to make a global statement. I'm just going to keep shrinking my neighborhood until everything is close enough to P that things will work. So potentially shrinking this neighborhood, I can assume that all the linear combinations of my original symplectic form and my new one, omega 1, are still non-degenerate. They're obviously closed because being closed is preserved by taking linear combinations. So I can assume that all of these linear combinations are symplectic on U. Now, it might be that if I chose my U kind of too big before, I will end up with points where there are degeneracies, but I can just throw them out. They'll only happen on closed subset, and so I can just throw them out. I can keep shrinking my U until I avoid all of those problems. And similarly, again, I might have to shrink U, but I can assume that it deformation retracts to P. So one way to think about this is I chose a metric, so I can assume that U is a very small ball in that metric, right? And since it's an open subset, it contains a ball of some radius, and I can just keep making that radius smaller. And if it's a ball of small radius, it'll deformation retract back to my point. Basically, you can think of it as like a ball up in the tangent space, and then it's obvious that a deformation retracts. All right, cool. So now I apply my Moser trick. And as I said, I really kind of like having this operator Q from before, because now I can just say, oh, I have a deformation retract. All right, well, then I can explicitly compute an antiderivative. I can look at Q of omega 1 minus omega, call that mu, and then I'm going to have this equation that omega 1 minus omega is d mu. Then connecting these two symplectic forms reduces to finding Vt such that when I contract it with the symplectic form omega t, I get minus mu, and I can do that using non-degeneracy. So in the notation I was using before, I would say that omega t sharp inverse of minus mu is the definition of Vt. So this is just kind of repeating this trick we had. And you'll note before I had, when I was talking about my compact manifold, I'd had to have a requirement that the cohomology class of my symplectic form doesn't change. Well, here on this small ball, because it's contractible, that's automatic, right? I didn't have to assume anything about omega 1 minus omega. It's automatically already exact. All right, cool. So using the Moser trick, I find my vector field, which tells me what to do, sort of tells me how to move my coordinates around so that the symplectic form omega 1, which was in the nice form I wanted, gets closer and closer and closer to being the form omega 0, which is the one I started with. So we have these VTs, we want to integrate them to a flow. And this is kind of a technical point. I don't know, I kind of debated how deep into this I wanted to get. Canis de Silva kind of just skates past it. But given that I kind of emphasized before that you really had to worry about your manifold being compact to make sure that there was a flow, here, the way you get around that is, again, you have the ability to keep shrinking your U if you need to. But the other thing that kind of saves us is that the way we constructed this, omega 0 and omega 1 at the point t itself are the same, right? I went out of my way to choose a basis of my original tangent space that was compatible with my symplectic form, right? And so I actually explicitly constructed omega 1 so it would be the same as omega 0 at the origin. It might change once I start getting away from the origin, but in the actual tangent space at the origin, they're equal. Okay, so that means that going through this Moser trick, right, I can assume that mu is 0 at that point. And so I can assume that VT is 0. And you might ask, well, wait a second, why is it that mu is 0? We'll go look at the formula for Q. The formula for Q involves integrating. If I'm staying at the origin the whole time and the form is always 0 there, you'll see my formula for Q is 0 in that case. So this vector field vanishes at the origin. And that's kind of the thing that saves us. So what we're going to have is we're going to have, here's P, here's my U, and my vector field V, well, it might do all kinds of wacky stuff. I don't know exactly what it looks like, but it vanishes at P, and it can't get big too quickly away from P, right? Everything in this picture is smooth. So there's a limit to how quickly I can increase from being 0. So I think it's plausible that I could just say, oh yeah, there's some small neighborhood around the origin that doesn't, where no points escape from my original U. I think you can go through a more detailed argument for this. I'm still kind of debating how much I want to say here. But you can choose a metric, and by scaling the metric, assume that the unit ball sits inside U. And as I say, the size of your vectors can't increase too fast. So now that I've chosen a metric, I can actually talk about the length of my vector field. And because everything is smooth, in particular, I'm going to have an upper bound on the length of my vector field, which is linear in the distance from this point P. So there's some constant L such that the length of the vector is less than L times the distance from P. All right. If you think about what that means, and in part I had to kind of write this out for my own satisfaction, that means if I follow an integral curve of this vector field, the speed at which my distance from P is increasing is less than L times what my distance already is. And so my distance can only be increasing by a factor of e to the L times time. So for each unit of time, the biggest factor I can increase my distance from the origin by is e to the L. And so if I start inside the ball of radius 1 over e to the L, I can't leave the sphere of radius 1. All right, so there's some small neighborhood U prime around P such that when I do the flow on U prime, I never leave U. And by this Moser trick, I also have that when I get to the end of the flow, when I get to rho sub 1, the pullback of omega 1 is going to be omega 0. So this means that I can define new coordinates on my U prime by pulling back the coordinates yi prime and xi prime. So my original coordinates xi prime and yi prime aren't right, but the Moser trick tells me how to correct them by using one of these flows. Sort of says, oh, you didn't have the right thing yet? Okay, well, let me tell you which direction you need to kind of change coordinates by to get closer and closer and closer to the actual form you want. All right, so that finishes the proof. Are there any questions?
Can you just go over how you got around the needing compactness by finding a flow that stays in U prime? Is that?
So the key thing is that at P, my vector field is 0. So, somehow the way to think about this intuitively is I'm trying to construct the flow. I can construct integral curves for some amount of time. And the thing I have to worry about is, oh, I hope they don't run off to infinity. That's kind of the thing that causes you trouble in the non-compact case. Well, if I'm actually at P, just staying at P forever is an integral curve. And then if I start really close to P, okay, maybe I'll start getting away from P, but I won't get away from it too fast. And I'm sure an actual analyst would have felt much more comfortable making this argument. I had to think about it last night for longer than I should have, but I think it's correct that, if the way to think about this is the length of the vector field can't increase too quickly. And what do I mean by length? Well, again, I said I chose some metric, and it isn't going to matter which metric I chose. There's some upper bound on some L such that the length of my vector can't be more than L times the distance from the origin. And well, I can only be moving away from the origin as fast as the length of my velocity vector. So sort of the fastest I could possibly be moving away from the origin is multiplying my distance by e to the LT.
Okay, thanks.
Which is, moving away from the origin pretty fast. But it's not infinitely fast. So, somehow I can get further away, but I can't explode off to infinity in a finite amount of time. And that's the thing I needed to worry about before. So, I should emphasize, right, the key kind of difference I'm using is when I had my forms on, when I was doing the original version of Moser, I didn't require that the forms matched at any point, right? Here, I'm really using the fact that my form doesn't change at the point P. So that's a much stronger assumption, which is what lets you kind of get around the compactness.
I have kind of an obscure question. What does it say about the metric if the metric already gives you Darboux coordinates? I guess it's not that obscure, it's just random. You get what I'm saying?
If you didn't have to do this correction?
Yeah, like if you had a metric such that the exponential map sort of gave you Darboux coordinates already.
Yeah, I don't know. I would have to think about it.
Random.
Yeah, my guess would be that wouldn't be very likely. but it's worth thinking about. They're sort of, yeah, we'll talk about this later when we talk about compatible complex structures, right? There is kind of a notion of compatibility between metrics and symplectic forms, but I don't think that would help you. I mean,
yeah.
I think the thing is, I would say is it would be really surprising.
Yeah, no, I'm just
chose
curious because it seems like you could do this also by deforming the metric into the right one, you know, sort of like one would give you the other, right? So it's sort of like, yeah, I don't know, I was just curious.
Yeah, I mean, with the metric, you don't have something like this Moser equation that kind of tells
Yeah,
you.
Right, that's true. Yeah.
I mean, yeah. So the short answer is I don't know. It doesn't. My intuition is that that will happen in certain odd instances, but I wouldn't.
Yeah, no, I was just curious what the property of such a metric would be. Like, it seems like it would be interesting to just find that out. But yeah, I don't know. Okay, thanks.
I don't know. What are people's thoughts on taking a break? Haven't quite. I kind of like the principle of taking a break, but now, especially 55 minutes in, I'm like, ooh, I don't know if I want to take a long break. So. Well, with all of these things, feel free to send me feedback. And yeah, maybe I'll pause another moment just to see if other people have questions. All right, so let me just make some small amount of commentary about this theorem. So one way to say this is that, again, it shows it's really hard to change a symplectic form. Symplectic forms, they kind of live in this splendid isolation. You can't really do much to them. But the other way I really like to think about this is, as I sort of said at the beginning of class, symplectic forms are kind of more analogous to flat metrics. And you can kind of debate whether that's so or not, but I would think of kind of the exterior derivative of the two form as kind of like a Riemann curvature tensor, right? So the Riemann curvature tensor is the obstruction to showing that in some small neighborhood, your metric is isometric to the usual one on Rn. If the Riemann curvature vanishes, you can do that. If the Riemann curvature doesn't vanish, you can't. And so similarly, this is sort of telling you there's this obvious symplectic form on R2n, and the exterior derivative of your is the obstruction to a two form looking locally like that one. All right, well, this will certainly come up again in the future, but let me move on and try to spend the last third or so class of talking about one other kind of important application of this idea. So this is not meant to be exclusive, but just to show you, okay, we can do this for comparing symplectic forms on the whole manifold. We can use the Moser trick for comparing symplectic forms just in a little neighborhood of a point. And there's one other kind of most natural way to do this. So if you look at the proof we did, you can use literally exactly the same proof to, instead of talking about one point, talk about any compact submanifold. So if I have any compact submanifold of a manifold M, which may or may not be compact, and I have two symplectic forms which agree pointwise on the submanifold. So they might be completely different away from the submanifold, but they're literally the same map on the tangent space on that submanifold. then actually there are neighborhoods where they're symplectomorphic. So the name of this symplectomorphism is phi, and I have the property that phi of omega 1 is equal to omega 0. And again, this is somehow you try to set up this Moser story, and everything goes okay as long as you're willing to, every time there's a problem, throw out more of the neighborhood around X, right? You can make these neighborhoods smaller and smaller and smaller until the proof works. And I'm not going to write that out because it's really literally the same. You can go read it in Canis de Silva. So the Darbuth theorem is a special case of this, where X is equal to a point. So you sort of do the part of the proof where I look in the tangent space and transport the symplectic form from the tangent space down to a neighborhood around my point, and then you can just say, oh, by the relative Moser theorem, I can do a symplectomorphism that makes these guys match up. One thing that's sort of worth noting here, before I just use that, well, little neighborhood around my point looks like a little neighborhood around the origin in the tangent space. So in particular, I can choose an open neighborhood that's contractible. In this case, I want to look at a neighborhood around all of X. And there's a nice answer for what that neighborhood looks like, given by what's called the tubular neighborhood theorem. And these neighborhoods are tubular in the sense of being awesome, but they're also tubular in the sense that if you imagine the case of like a circle inside R3, this neighborhood is going to look like a kind of tube around this guy. So this is kind of the picture to have in your head. But we have to be careful about what we're going to look like, right? So the answer around a single point was a neighborhood of the origin in the tangent space. But now that we have a submanifold and we're looking at a neighborhood around that, well, you're going to have the submanifold and then the sort of perpendicular directions. Well, that's not going to look like the full tangent space. It's going to look like the tangent space of the ambient manifold minus the tangent space of the submanifold. And there's a name for this, which is the normal space. So I look at the tangent space of my bigger manifold M, tangent space of my smaller manifold X. I look at the quotient and I get a vector space that sort of tells me about what the perpendicular directions look like. If I think about this on X, it'll give me a vector bundle on X. So I can think of the vector bundle whose fibers are the tangent spaces of M on X. That's the pullback vector bundle from the tangent bundle of M. You can think about the tangent bundle of X as a sub-bundle of that. And then I can take the quotient of vector bundles. And this normal bundle is denoted NX. Again, I'm following Canis de Silva. This will be different for different authors. I think some people might write NXM. Well, I just be careful about, somehow this normal bundle, it depends both on what the submanifold and the ambient manifold is. And quite often people want notation that includes both of them. Canis de Silva just writes NX and leaves M as understood. So what happens in general for X? So when I say X inside M is above, I mean that X is a compact submanifold and M is a manifold, but not necessarily compact. then X is going to have a neighborhood that's diffeomorphic to a neighborhood of its inclusion into its normal bundle. So here, X is a diffeomorphism. All right, so this is sort of a useful thing to know. Whenever you have a submanifold, whatever information is going on very close to that submanifold inside the ambient guy, you can model using this normal bundle. So the sort of questions you might think about here is, if I have a submanifold, how can I sort of deform it inside M to be a close but not exactly the same submanifold? That's going to correspond to a section of the normal bundle. It's the kind of ideas one uses. All right. Any questions? So this is sort of, this idea that a little neighborhood of a point always looks like the tangent bundle, but kind of souped up to think about a family of points, all the points in the submanifold together, and then kind of accounting for the fact that they can see each other. And you have to eat up that part of the tangent space. Oh, I see there's a chat. It's probably been around for a while, but let's see. Oh, Hugh thinks it's a good principle. I wonder what principle he was talking about.
Sorry, that was you said the principle of taking a break. I said I thought that principle was a good one.
Oh, okay. Well, I don't know. There's also the principle of finishing on time, so we'll see how that goes. So the other really interesting case to look at, where you can compare symplectic forms, is when your submanifold is Lagrangian. We already discussed Lagrangian submanifolds are some of the kind of the most interesting concept in symplectic geometry. So sort of it's a natural thing to look at, like what does the story look like when you apply it to a Lagrangian submanifold? So first, there's something interesting to be said about what the normal bundle is. So if I have a symplectic vector space and a Lagrangian subspace, then I can use the symplectic form to identify this space with its dual. And so I have a map of L into this space as the usual obvious inclusion. And I have a map to L dual, right? So it's worth always remembering the dual of a subspace is a quotient of the dual. It's the dual space modulo the functionals, which are 0 on that subspace. And because L is Lagrangian, so you can actually say L is Lagrangian if and only if this sequence is exact, if and only if the image of L is exactly the kernel of this map to L dual. So we end up with a canonical isomorphism from L dual to V mod L, which is, you can think of as just take an element of V, pair it with stuff in L. It's not going to care which coset, adding an element of L won't change anything that happens with those pairings. So you get an isomorphism between V mod L and L dual. And it's worth remembering this is canonical, given that we fixed the symplectic form. So if I have a Lagrangian subspace, I can apply this observation pointwise with V being the tangent space to all of M, and L being the tangent space to the submanifold X. All right, so that L dual, that becomes the cotangent space to X. And V mod L, that's exactly the normal space. So I get that if my submanifold is Lagrangian, the normal bundle is automatically the cotangent bundle. So I'll probably remind you of this from time to time. One way to say this is, to a Lagrangian submanifold, it always looks to that submanifold like it's the zero set of a cotangent bundle. That's kind of a universal model for what Lagrangian submanifolds look like if you only look very close to the submanifold. But I'll just mention, this is only a diffeomorphism. So we can pull up this diagram from the tubular neighborhood theorem, and we can say, aha, I have a theorem that there's a diffeomorphism here. But if my X is Lagrangian, then this guy has a symplectic form because it's a cotangent bundle, and this guy has a symplectic form, so it's an open subset of a symplectic manifold. And I can reasonably ask, well, probably if I wasn't paying any attention, my diffeomorphism wouldn't be a symplectomorphism, but maybe I can make it be a symplectomorphism. And in fact, it's a theorem that I can do that. So there's this Weinstein Lagrangian neighborhood theorem. So if I have any symplectic manifold, again, I'm not assuming compact, and a compact Lagrangian submanifold inside it, then there's a neighborhood of, so this U, that's inside, oops, inside M, and a neighborhood of X inside the cotangent bundle, which is the same as the normal bundle, and a symplectomorphism between them. So if I'm careful about what I'm doing, I can actually upgrade this tubular neighborhood theorem to be a symplectic tubular neighborhood theorem. So this is another reason that Lagrangian submanifolds are so special. They're kind of local, the local behavior around them is kind of completely determined just by the fact that they're Lagrangian. All right, so how do we actually prove something like this? Well, I think the tempting thing to do is to say, aha, we know about this Moser trick. So we sort of, every time we've done this, what do? We kind of start with the best approximation we can get, and then we can say, oh, probably the symplectic forms aren't going to match. Oh, well, I can construct a flow which gets them closer and closer and closer to matching, and eventually I'll get the symplectomorphism that I want by using this Moser trick to construct a vector field and then integrating that to get my symplectomorphism. And eventually we'll do that, but you have to be more careful. So Canis de Silva deals with this in a way I don't quite like, using the Whitney theorem. So I'm gonna give you a slightly different argument. It's kind of morally the same, but I think one kind of applies the idea a little bit earlier. So I can construct a diffeomorphism from this tubular neighborhood theorem. And so my T star of X has a symplectic form on it. I can pull that back and get an omega 1. And I have my original omega 0, the inherited form from it. And I want those to agree. And I want to use this relative Moser theorem to make them agree. But I have this problem, which is I might not have the hypothesis that I need for the relative Moser theorem. I might have that even on my manifold X, I might get that omega 0 and omega 1 are not the same. And the reason is I actually have a bit of freedom in how I set up my tubular neighborhood theorem. And if I do it wrong, I won't get something that's even a symplectomorphism, like kind of in that even gets the symplectic form right on X itself. And the reason is that when I do this tubular embedding, so if I look at the tangent space to, maybe I'll go back up here. If I look at X inside N of X, and I take the tangent space at that point, so tangent space to N of X at X, that's isomorphic to the tangent space of X plus the normal space at X, right? Whereas in M, I have an exact sequence from the tangent space of M that maps down onto the normal space with the tangent space of X as a sub, but there's no canonical splitting of this exact sequence. So somehow the thing that I have to be really careful about in this Lagrangian neighborhood theorem is actually secretly, when I do the tubular neighborhood theorem, I'm choosing a split. And the usual way that people do this is they pick a Riemannian metric and they say, okay, this T of X, that's a canonical thing. And the splitting I choose is the one into that guy and its orthogonal complement. Right, so, you know, I have to choose a splitting, and this is really a choice, and I will get sort of a different tubular embedding if I choose a different splitting. And the sort of thing that I think Canis de Silva should have done, but she kind of gets around in a slightly different way, is you have to choose the right split. So I have to do this, and I have to do it in a way that varies smoothly. So I need it to actually be a sub-bundle. And I will just ask you to accept, I don't think it's hard, but you have to make some noises about the inverse function theorem, that you can make the tubular neighborhood theorem work with any splitting that you choose. So like if you go and look at a usual proof, they will use the splitting that comes from a Riemannian metric. But if you sort of do that and then choose a different complement, you can still make the different complement work. And again, it's basically the inverse function theorem that you can construct a map from the normal bundle that matches the splitting you want. The derivative is going to be an isomorphism on X. And so the map has to be a diffeomorphism on a neighborhood. All right. So yeah, usual method is to pick a metric. And the thing that could cause omega 0 and omega 1 to be different on my submanifold X is this complement I pick might not be Lagrangian. So I'm going to get my forms right if and only if I choose this Z to be Lagrangian at every point. It's worth sort of thinking through why that is, but you should at least believe, oh, when I look at T star of X, right, the 0 section is a Lagrangian submanifold, and the fibers are Lagrangian submanifolds. So there, the tangent space is written as the direct sum of, at a point in the actual 0 section, the tangent space is a direct sum of 2 Lagrangian submanifolds. And I have to kind of carry that over into my manifold M in order to get this to work. So somehow exactly the thing that can be going wrong with the symplectic form on the submanifold X is I'm matching up that fiber direction in the cotangent bundle to a subspace I haven't made sure is Lagrangian. All right. So I then have to just use this bit of linear algebra trickery, which again, Canis de Silva includes, but she puts it in a slightly strange place, and I think her notation for it is very unpleasant. But the important idea is there's a canonical way to go from a random old complement that might not be a Lagrangian to a Lagrangian one. And one that in particular is going to be sort of very smoothly as you move around. So it's going to give you a Lagrangian subbundle. And let me just write this down because it's actually sort of a nice slick little piece of linear algebra. So my original symplectic form induces an isomorphism from the dual of this complement Z, so that's the co-normal space, to the tangent space of my submanifold. And the reason for this is that the tangent space of my submanifold is Lagrangian. And if I have any transverse subspace to a Lagrangian, I get a non-degenerate pairing between them. Sorry, not transverse, complementary subspace to a Lagrangian. I get a pairing between them. So I can define a map nu from the dual of Z to this tangent space to X by the rule that the symplectic form on nu of beta, where beta is an element of the dual, paired with Z in my ZP, is the same as pairing that functional beta with Z in the usual way that Z dual and Z pair. So this is sending an element of the dual of Z to the unique element of the tangent space of X that pairs that way under the symplectic form. All right, and then the way to get a Lagrangian complement is to start with an element Z of my original complement, and then I correct that by contracting it with the symplectic form. So that gives me an element of the dual of Z. And exactly the problem, if I'm not Lagrangian, the thing I have to worry about is that that guy might not be zero on Z, right? I want Z to be Lagrangian, so that guy being non-zero is the problem. So I think of this contraction as an element of the dual of Z. I feed it through this map to get an element of the tangent space to X, and I subtract half of that from Z. And that half is because I'm going to pair two things. I'm going to get the same correction twice, so I only want to insert a half, so I only correct the right amount. And I've written out here exactly what happens. So it's just a little linear algebra computation, but it's a really important observation that having any complementary subbundle to a Lagrangian, I can correct that to be a Lagrangian complement. So if I now use the splitting of the tangent space of M into the tangent space to X, and this corrected Lagrangian complement, then I can construct one of these tubular neighborhood diffeomorphisms, which respects the symplectic form at points actually in X. So I'll get that for P in X. The original symplectic form agrees with this pullback one. And so it follows, using the relative Moser theorem now, that I can take my omega-1 coming from the tubular neighborhood, I can take my original symplectic form, and I can connect them using this usual trick of construct the vector field, integrate it to get the symplectomorphism. Whew. All right. Any questions? So, I should maybe just emphasize, this is actually very similar to this Darbuth theorem. We just had to do a little bit more work in this stage of going from the tangent space to, well, not exactly coordinates, but, matching up with the cotangent bundle on a neighborhood around X. Yeah, Josh.
Okay, so I was saying that okay, the symplectic W naught induces an isomorphism from ZP star to TP of X.
Yeah.
And is ZP the tangent space to the Lagrangian?
No. So yeah, no, it's no problem. So in this tubular neighborhood theorem, in order to construct, so yeah, let me say like a tiny bit more about what's happening here. So, how do I do this tubular neighborhood theorem? I have my tangent space to the whole manifold, and I split that up as a direct sum of the tangent space to the submanifold and something complementary.
Mhm.
Okay.
Oh, ZP the complementary space then.
Yeah.
Okay, that's
Yeah. And right, so what I'm going to do is I'm going to take the normal bundle to X, right? And I can think of this as also the total space of ZP. So the point is I have to take the normal bundle and choose a specific embedding of it into the tangent spaces to the ambient manifold M at each point in X, right? So this normal bundle, that's by definition things in X, and then N, which is in NX. X. And so, the way I use this ZP is that I can map this normal bundle into, I'm just going to write here the union of the tangent spaces to the points in X. But I'm taking the tangent space inside of all of M, right? And when I do that, I have to choose an embedding of the normal bundle into the whole tangent space. There isn't a canonical way to do that because the normal bundle is defined as a quotient. Right? So I have to construct a map like this, and then I hit that with the exponential map. Right? And so the thing I was claiming is that kind of any way of choosing that complement in a smooth way will get you a tubular neighborhood. Because if you think about what's happening on derivatives here, you're getting an isomorphism on tangent spaces at all the points in X. But choosing this inclusion exactly requires choosing a complement to the tangent space of X. Do you have another question, Josh?
No, thanks.
Great.
I have a small question. Sorry.
Mm-hmm.
This, you might have covered this earlier, but if I have a Lagrangian subspace of a symplectic vector space, like how many Lagrangian complements are there? Is there a unique one, or is obviously not any complement is Lagrangian, because then we wouldn't have had to do all this. So I'm just, you know what I'm asking?
No, there are many Lagrangian complements. Yeah, I mean, I guess it's somehow hard to answer this, right? There are lots of them, but many fewer than kind of all complements, right?
Okay, all right, no, that answers my question actually, because I was
yeah. Yeah, no, it's very much not unique. You should think of it as kind of a similar thing where it's easy to show that one exists, but the kind of the way you construct it is very not unique, right? One useful way to think about this is one way to construct a Lagrangian complement is you choose your Lagrangian, and then starting with any other vector that isn't in that Lagrangian, you can complete that to a Lagrangian complement.
I see. Sort of like
Right.
Graham-Schmidt.
Yeah. So, right.
Well, not really.
And, you know, somehow like what this operation here tells you, I mean, you should think of this as kind of Graham-Schmidt as well, right? It's sort of saying like, oh, I want these guys to be orthogonal to each other. Well, I need to subtract off some other things to make that happen.
Yeah. Yeah, because the confusing thing for me is that if you take the definition of orthogonal from inner product land, then a Lagrangian subspace is orthogonal to itself, right? So it's like you can't just right. So you can't just like take the dual or something, or you know, take the anyway.
No, there's
Right.
no canonical way to construct a Lagrangian complement. Yeah, maybe one good answer to your question is the space of symplectomorphisms which preserve the Lagrangian acts transitively on the set of Lagrangian complements. So all Lagrangian complements look the same up to symplectomorphism, but there are a bunch of them.
Good fact.
And right, one, you know, yeah, the one way to think about this is, yeah, let me not worry about it, but yeah, there are a lot of them, and they all look the same up to symplectomorphism, because if you have a Lagrangian complement, if you have two complementary Lagrangian subspaces, you just choose dual bases of them, and you will get a standard basis for the symplectic form. So for the symplectomorphism group of the linear symplectic thing, so I mean linear symplectomorphisms, acts transitively on the set of pairs of Lagrangian of complementary Lagrangian subspaces.
Transitively on pairs. Okay. Thank you. Interesting.
Yeah. With the stabilizer being GLN. Basically, if I fix two Lagrangian complements, the only thing I can do that preserves both of them and is a symplectomorphism is to do one linear transformation of one and the dual linear transformation of the other. So the space of pairs of complementary Lagrangian subspaces looks like the symplectic group of dimension 2n mod the general linear group of dimension n. It's big space. Yeah, Josh.
So given a particular Lagrangian, like just a Lagrangian subspace at a point, there's, I guess, many different complementary Lagrangian subspaces, right?
Mm-hmm.
So I was curious, how much like freedom is there in varying that complementary subspace? Like I suppose they could form like.
Well, as I said, you know, one thing which sort of isn't a detailed description, but gives you a sense of how big it is if you have a Lagrangian, you can start with any guy not in that Lagrangian and construct a Lagrangian complement containing it.
Okay.
Right. You know, basically, right, you pick something not in L, and then you want to just keep on adding things that aren't in the span of L in the vectors you picked thus far, and aren't, you know, are perpendicular to the guys you've chosen thus far, right? So, you know, somehow, right, if you start with a generic element of your vector space, and then choose a generic element that's perp to that, and then choose a generic element that's perp to those two, and choose a generic element that's perp to those three, eventually you'll get a complementary Lagrangian subspace. So that
But the
just
problem
gives
is
you a
like,
sense.
what do you mean by perpendicular?
Sorry, not symplectic perpendicular. Right.
Yeah,
So
right.
the
Yeah, so
if you've
so that
chosen
omega
K
is
of
0.
these,
Yeah,
there's going to be a space, an 2n minus k dimensional space of guys perpendicular to all of them. And I'm going to remove a k plus n dimensional subspace from that and say you're not allowed to use that. And you can choose anything else in what's left.
sure. I see. I see.
So like it's a big space. You have a lot of choices. So it's less, so that's actually a good illustration, right? If you're trying to choose a vector space complement, you would just choose n generic elements of the vector space, right? And now it's, no, the ones you've chosen thus far constrain your choices. You're choosing from a smaller dimensional space, but you're still choosing from a non-empty vector space minus a lower dimensional vector space. All right, I'm over time now. So let me not get too much into the consequences. They're discussed in a lot more detail in Canis Silva. The one thing I'll say is, right, so up to kind of things that you can see using symplectic geometry, Lagrangian submanifolds always look like the zero section of a cotangent bundle. So, one kind of interesting thing I just wanted to spotlight, that means that Lagrangian submanifolds, which are very close to your chosen one, so you have a Lagrangian submanifold X, and you want to think about what happens when I deform that. I get some X prime that's sort of pretty close. Canis Silva actually talks about like, oh, C1 closeness, etc. Let me not worry about those details, but it looks like a Lagrangian submanifold that's close to the zero section in T star of X. So those are given by closed two forms. So this means that sort of what nearby Lagrangian submanifolds look like exactly looks like the space of closed two forms. One good example is if your Lagrangian has vanishing first homology, then closed forms are always exact. So any nearby Lagrangian comes from the differential of a function. And you can answer questions like, well, what do intersection points between my original Lagrangian and my new one look like? Well, they come from critical points of your function. So in particular, you might ask, could I find a nearby Lagrangian that doesn't intersect mine? And the answer is, yes, if you have a non-vanishing closed one form. So for example, if you're a circle, but no, if you have vanishing H1, because that means you're exact, and any function has critical points on a compact manifold. And in fact, it has at least two critical points. It has exactly a minimum and a maximum. And depending on the topology of your manifold, it might have to have much more. Right, by Morse theory, you can actually bound that below by adding up the dimensions of the different homology groups. You have to have at least that many critical points. So this is just kind of the stuff you can start to see using this fact. And it's valid for any symplectic manifold, but it's sort of only telling you stuff about things that happen very close to that Lagrangian. You don't have any control about what happens further away. All right.
Oh, sorry. We're a little over time, but I can delay my question. But I was just saying, like, why would the space of nearby Lagrangian submanifolds be like the space of closed two forms? Like, is it like?
Sorry, I meant closed one forms. Closed one forms.
Closed one form.
So, sorry, let me actually get my pen. I dropped it under my desk.
Closed.
So, yeah, I should have said one forms. I'm sorry. So the reason is I think you joined the class a little late, so you might not have actually been here when we discussed this,
Yeah,
right?
it's true.
So if I have the cotangent bundle of X, then that has a map down to X, right? And if I have some other Lagrangian submanifold in here, then that has an induced map to X. And if I'm sort of close to X, then that should be an isomorphism. All right, and then, well, that means that each for each element of X, there exists a unique X, C of X, which is in X prime, where C is a covector, right? That's just the point of the cotangent bundle that it is. And I can think of X goes to C of X as a one form. And we proved the theorem that X prime is Lagrangian if and only if this one form is closed.
I see. Interesting. Thank you.
And I mean, the reason is that if I take the canonical symplectic form on the cotangent bundle and I restrict that to X prime, and then that is the two form dC, identifying X prime and X. So it's going to vanish if and only if the one form is closed.
Very nice. Thank you. I'll look up that I'll look up that proof again myself. Thank you.
And I use the minus sign. That's minus that. Yeah, I mean, I think if you just like kind of go through, we didn't sort of do this directly in coordinates, but I think you could, right? If you really kind of thought about what the heck was going on. Yeah, it might be interesting to actually kind of directly check that in coordinates. The way we prove this is that omega is minus d alpha, where alpha is what we call the tautological one form. So it's ci dxi in any coordinate system. And this has the property that if I restrict alpha to X prime, I get Xi on the nose. So when I restrict it to the graph of a one form, I get that one form. So this equation up above is just taking minus d of this equation here.
I see. Thank you. Yeah. So a section of a cotangent bundle is Lagrangian if it's closed when you think of it as a one form.
Yeah, exactly. Yeah.
Very cool. Very cool.
Right. And this is something that somehow happens a lot when you have something you can think of as a half-dimensional submanifold of a symplectic manifold. It's sort of always like being Lagrangian is some special property about the thing. So, I mean, another kind of place where Canis de Silva talks about sort of applications of this is that So if I have two symplectic manifolds, I mean, let's talk about the same underlying manifold just to make my life easier. If I have two different symplectic forms, then a diffeomorphism from M to M is a symplectomorphism. If its graph is a Lagrangian submanifold. So I have a graph of gamma. This is all the pairs of the form phi of M. And I think of this inside the symplectic manifold M cross M, and then pi 0 pullback of omega 0 minus pi 1 pullback of omega 1. And so this is sort of, I'm taking the product manifold, I'm almost constructing the kind of obvious way to put two symplectic forms on the product, but I have this funny minus sign that shows up. Symplectomorphisms, which are close to the identity, match up under this sort of Lagrangian embedding theorem, right? We sort of think about, what is the stuff near the diagonal in M going to look like? What are the Lagrangian submanifolds close to this guy? Correspond to Lagrangian submanifolds. Close to sorry, not close to the identity, close to phi. Close to gamma phi. And again, that means they look like closed one forms on my original M. So just as I was able to make this conclusion about intersections between Lagrangian subspaces, if I apply this with phi is equal to the identity, this implies that, if H1 of M is equal to 0, symplectomorphism is close to the identity. Have two fixed points. And more generally, there's a bound in terms of Betti numbers. And this is all discussed in more detail in Canis de Silva. Whew. All right, so let me stop recording.